Hi, I'm Ahmed Daud, and in the last session we have started regularization. Regularization is a concept or method to avoid overfitting. Now, how we can avoid overfitting? We have figured out if we can add some penalty to the cost function, then we can avoid overfitting. Okay, we have seen that uh, if we will add some penalty to the cost function, let's say previously we have cost function mean square error. Then if we will add some penalty to that mean square error function, so in that case we can control the uh, overfitting. Okay, this lambda factor will control how much penalty we should have to add in the cost function. Okay, I have told you that well, let's say without regularization during training, our model is trying to, or during training process, our model or our algorithm is trying to find such type of error, mean square error, or find such type of parameters where mean square error is minimum. Okay, no matter how larger the parameter values we are getting. Okay, so if we have to control parameter values, or you can say coefficient values during the training process, then we have to penalize our cost function that we previously had. Okay, that's why we have added penalty. Okay, so we have discussed that two types of penalties we usually add. One is L2 squared L2 penalty, and the second one is L1 penalty. So in this session, first we will start from the lasso regularization, in which we add L1 penalty to our error function or to our cost function. Okay, so in the lasso regularization, our penalty will be like that. Okay, we have penalty theta absolute of theta 1. Let's say if we have two features, okay, so penalty will be theta 1. Keep in mind, these are the theta 1 plus absolute of theta 2. Okay, if we have two independent features, okay, so theta 0 is coefficient. So oh, okay, theta 0 is actually intercept, and theta 1 and theta 2 are coefficients. So we don't have to regularize our intercept. So that's why we have not added in the penalty. Okay. So now we will try to visualize that, and we will see how lasso regularization have an impact on actual or you can say on the uh, how lasso can avoid overfitting, and it has impact on the error function that we previously have. Okay, so here first of all I will show you here. Let's say, okay, so here usually we have that type of error function. Let's say we have two coefficients here, theta 1 on the x-axis, let's say theta 2 on the y-axis, and mean square on the z-axis. Okay, if we visualize, our graph will be like a ball shaped, our plot will be, and if we will run the gradient descent algorithm, then our algorithm will be move in the direction where we will find our minima of that plot. Okay, or minimum, where we find minimum SSE. Okay, sorry, here we have mentioned mean square error, so minimum MSC. If we will see this plot from the upward, okay, from the upward direction or from the z axis, okay, our plot will be like that. Okay, this is theta 1 in that direction. I will make this. Okay, so theta 1 is in that direction, theta 2 is in that direction, and our plot, if we are looking from the upward, okay, from the z axis, so here we are trying to reach that position where our mean square error is minimum. Okay, so here you can say our cost function was g of theta is equal msc theta. Okay, that we previously we had that type of functions before the regularization. Now, if I want to visualize my penalty function, let's say penalty function, let's say you can say g of theta is equal to penalty. Okay, some penalty I have here, theta 1 is growing in that direction, theta 2 is growing in that direction, and penalty is growing with the z-axis. Okay, I have this type of plot here. Okay, now if I will see this plot from the same data I have seen the previous plot of MSC, I will see from the z-axis to this plot, my plot will be like the diamonds here. Okay, like these diamonds are. Now, if I will run the gradient descent algorithm on the same plot, so my I will move in that direction towards my penalty equal or to minimize my penalty. Okay, you have seen this mean square error plot I have plotted multiple times. So I want to visualize you that plot also. If I will show you here, this one. Okay, you can see here. You can see if I will run that. Okay, now you can see if you will plot, let's say on the red axis you have theta 1, on the green axis you have theta 2, and on this blue axis you have your penalty. Okay, your uh, penalty for L1 penalty will be looks like that. Okay, like this. If you will see from the upward in that direction, then this is your theta 1, this is theta 2, and your penalty will be of diamond shape. Okay, like here I have shown you uh, this one, as my drawing is not so good. So anyways, here you can see this will be like a diamond. So now if I want to see these two plots, plot of penalty, plot of my mean square error on the same plot, on the same graph. So it will be like that. Okay, here you can see this is a j of theta. This is a plot of mean square error, you can see, and this is plot of penalty, which is in our case is theta 1 plus theta 2. Okay, so on this axis you can say theta 1 on this axis and theta 2 on this axis. Usually we have to reach in without regularization, we have to reach at this position. Okay, to minimize our error. Like if we have error in this way, so we have to go in the bottom of that mean square error bound to make our error minimum. Okay, we find such parameters where our error minimum, and in this case this one. Now as we have added some penalty to that function, now our function is not this one. We have added some penalty to that function, so that's why some penalty we have added here with some value of, let's say, lambda. Okay, so we have some added some penalty. So now our g of theta will be minimum. Previously, our g of theta was minimum at this position. Now our g of theta will be minimum where our function, if I will show you, it will be minimum at this position where it is, yeah, at this position where it is overlapping with our penalty. Okay, more visually, if I will show you here, let's say you have again theta 1 in this direction and theta 2 on this direction, and these background contours are these are the background contours that we have here. These are okay. These background contours are actually the mean square error, and the diamonds that on the foreground or upward you can see here are the of the functions of penalty. So here you can see when usually we have to minimize our mean square error. Our gradient descent algorithm is working in this way, and it goes to the direction of minimizing the mean square error. Okay, when we have to minimize our penalty, it has to go in that direction. in case of L1 penalty. Okay, so it will try to make the zero the coefficient which has value lesser as compared to other coefficients. Let's say here theta 0 is lesser. Oh, sorry, theta, yeah, theta 0 has less value and theta 2 is height, so theta 2 is maximum as compared to theta. This is theta 2, this is theta 1. So theta 1 is less than as compared to theta 2 here. So it will first make theta 1 equal to 0, and then it will move in the direction of making theta 2 equal to 0. Okay, when you are running the gradient descent separately on the penalty algorithm, okay, on the penalty function. Okay, so when you will add both, like in our case of regularization, when you will have this type of function, mean square error plus some penalty. Okay, here you have lambda, and let's say lambda value is 0.5. Okay, now you will have function like that. Okay, you have not much smoother leaps here. You have like this type of function you will have. Now again, when you have to minimize that function, that g of theta, you have to minimize that g of theta, then again, and you have added L1 penalty in your function. Here you have penalty which is L1. Okay, now in the same way, your algorithm, if you will run gradient descent again, it will move in the direction. First it will try to, like here again you have theta 1, here you have theta 2. First it will make theta 2 is equal to 0, like in this case it is making theta 2 is equal to 0. Then it is moving in that direction of to find the minimum point. Okay, now you have theta, here you will have some value for the theta. Okay, so here you can see that in the case of L1 penalty, our some parameters are that are in lesser uh, magnitude as compared to other coefficients. L1 penalty makes or try to make some parameters or some coefficients equal to 0. Okay, or you can say Lasso or L1 penalty make some coefficient equal to 0, the coefficient for lesser important features. Okay, and you can see here, if I will show lasso regularization, if you will see the lasso, what is lasso? Lasso is actually least absolute, least absolute and shrinkage and selection operator. Okay, when you will see on the, like on some books, the what is the abbreviation of lasso, here you can say least absolute shrinkage and selection operator. It also works as a selection operator because it make the parameter values equal to 0 for the less important features. Okay, now you have seen that how when you will add some penalty to your error function, then you are not actually getting the mean square error. Like here in that case you can see actually your minimum mean square error is this one, but when you have added some penalty you will get this as a minimum. Okay, now there is some, this is the difference between your actual mean square, minimum actual mean square is this one, this point, and but in when you have added some penalty you will have this. Okay, when you have added some penalty to your error function you will have that as your minimum n. Okay, as your minimum cost function. Okay, now you have seen you are getting such type of along the way you are minimizing your error, you are also trying to minimize your parameter values. Here you have seen, okay, you are trying to minimize your parameter values, and you want such type of parameters which are giving you less error and also less values of which are also having less values. Okay, now when you are doing, in other ways you can say, when you are doing some regularization, you are just not considering the to minimize the mean square error, you also consider how you can minimize your coefficients also. So in the case of L1 penalty, you, you are you are making some parameter values equal to 0, which are lesser in the magnitude, or you can say for the less important features you make the coefficient values equal to 0. I have told you in the last session also that some we do regularization, and in some cases we are making our parameters values smaller, or in some cases we do regularization when we make some parameter values or coefficients equal to 0. Now Lasso has a power that it can make some coefficients equal to 0. Okay, now we will try to explore what is ridge regularization. So in the case of ridge regularization, we will add L squared L2 penalty squared L2 penalty in our cost function. Okay, so here if I will show you here how it will look like. Yeah, this one. So here you can see we will add this into our cost function, theta 1 square plus theta 2 square. Okay, so if you will see here in that case, in the case of L2 penalty, our cost function will be in this way, mean square error plus lambda theta 1 square plus theta 2 square. Okay, now how it works actually, we will see. Now here you can say this is our original plot when you will see from the direction up, from the upward direction. Okay, from the z-axis you will see your error function plot, mean square error. You can see in this axis theta 1, this is axis theta 2, and when you are looking from the upward your graph, then your graph will be mean square error like that. And this is your uh, plot of penalty. Okay, penalty which is in our case is theta 1 square plus theta 2 square. Okay, I will show you this one like we have seen the lasso case. Here you can see, you have seen here when you I have plotted my graph is like that here. Okay, if I will take so here the graph is like that, graph of the penalty is like that in the form of circle. Okay, the red axis you can say is theta 1, the green axis is theta 2, this is theta 1, this is theta 2, and this is your penalty. Actually, when you are running your algorithm separately, when you have function without regularization, your force function mean square error, your algorithm work in this way, and you will go to the words of minimum mean square error. Okay, when you have just your function in which you have just penalty, which is theta 1 square plus theta 2 square, you have no mean square error. So your function will be, if I will show you here, your gradient descent will work in this way. Okay, if I will not in this way, it will go in this direction, and in this way you will minimize your penalty. Okay, but when you will add both of them, your cost function will be, if your cost function is in this way, mean square error plus some penalty, which is uh, if I will remove here, and I will add lambda theta 1 square plus theta 2 square. Now in that direction, your minimum g of theta, okay, your minimum g of theta, okay, before you have seen your minimum g of theta in the case when your mean square error is this one. When you have g of theta as a penalty, then your minimum g of theta is this one. When you have mean square plus lambda into some penalty, then your minimum value will be like in the case of lasso, your minimum will be this one, where they are overlapping to each other. This will be your minimum. Okay. Again, this is not original your minimum mean square error. Your this is a little bit away from your original mean square error, and it depends upon the value of lambda, how much value of lambda you are adding. If your lambda value is higher, then you are more away from your actual mean square error. Now, it is the case when you have you are visualizing both mean square error and penalty separately. Okay, like here, you are visualizing separately. This is the way of gradient descent of your mean square error. This is mean square error, and this is the way of minimizing your gradient descent algorithm, minimizing your penalty. Okay, when you are visualizing separately, when you will add both of them, you will have that type of function. Okay, now here you can see your gradient algorithm will work in this way. Okay, now it is little bit. In that case, you can see your at this point you have this one from this square, like this is square, uh, 1, 2, 3, and fourth. 1, 2, 3, and 4. Here it is at the corner. Yeah, this is your original mean square error. But when you have added your some penalty, your cost function, now you will your minimum cost function will be away from your original at this position. Okay. Now if you will run algorithm, your algorithm give you minimum cost function at this point. Now at this point you have theta 1 and theta 2 values, as in this case theta 2 is lesser. Like if you will see here, theta 2 is this one and theta 1 is from this to this. Okay. Now here you can see your theta 2 is lesser but not equal to 0 in the case of reach. Okay, reach regularization makes your coefficients approaches to 0 but cannot make exactly equal to 0. But in the case of lasso, you have seen that lasso has a power that it can make your coefficients equal to 0. Okay, so sometimes we really need lasso regularization instead of ridge regularization when we have to make our model will work better when we have to make some coefficients equal to 0. Okay, and in some cases ridge regularization works better when we don't need to make the coefficient 0, we have to make coefficients smaller. Okay, now this is lasso and ridge regularization. Theoretically we have seen. So practically, till now we have seen the linear regression. If I will write here in this way, okay, by this, we have, we have implemented our uh, linear regression having one variable, multiple regression having multiple variable, polynomial regression in which we have polynomial features. We have used sklearn dot linear model, linear regression class. Okay, this class we have seen used till now. This linear regression class used the method of closed form solution. As I told you, there are two methods in the case of linear regression. We have like to train linear regression to find the parameters we have seen during training. For the training purpose, we have two methods: closed form solution and second method is gradient descent. Okay, a closed form solution we also called it as normal equation. Okay, normal equation. So linear regression class, I have told you that linear regression class has used this method. Okay, this method it will use. But when we will implement our um, lasso and ridge regularization has both option when we will use ridge from sklearn and lasso from sklearn. Okay, ridge has both option that it's up to us if we want to use closed form solution or if we want to use gradient descent. But in the case of lasso, we there is a one option which is option of gradient descent that we can use gradient descent. Okay. Now, when we will go towards the part of code, we will see the lasso and ridge regression, practically how we can implement them in more detail. Okay. Now, here you have seen that these regularization we are doing on the regression algorithm. Okay. Here the algorithm which we are discussing till now we have started the module of supervised machine learning and regression part we have started. So we will implement lasso regression and ridge regression because when we are doing regularization, some classification algorithms, then in that case we have some different type of we like in the logistic regression, you have lasso and ridge as a your parameter values. Okay, so in the next session we will discuss these in more detail when how we can implement them in the code. So for now, thank you.